He has designed many chemical products, including environmentally friendly cleaning and separation solvents, new lubricants, enhanced thermal storage materials, improved jet and rocket fuels, and many other
Nice.
things. He also taught a graduate course about chemical product design as an adjunct professor at Columbia University for 5 years. Dr. Joback holds a bachelor's degree in chemical engineering from Stevens Institute of Technology, as well the master and doctor degrees from MIT. And he's currently president of Molecular Knowledge System. Okay, it's a very nice pleasure to have you here, Dr. Kevin, and you have the time that you may need, and
Great.
after people can ask you. And if somebody wants to make questions right now, we just write in the chat, and then we come back after his presentation. Okay.
All
Thank
right.
you very much.
Good. Well, Veronica, thank you very much. And everyone else, thank you. I hope everyone is doing well. And really, thank you for the opportunity to talk about something I really enjoy, which is designing chemical products, and specifically using physical property models to design chemical products. I've been fortunate, as you heard, I've been doing this for about 30 years. And so I just wanted to share some of the experiences and lessons that I've learned. I have some goals for the presentation. One of the things I really want you to do is understand a bit more about chemical products, see how chemical products are designed, and really come to understand and enjoy chemical products. I mean, chemical products are amazing. Things like shaving cream. You may never think about it, but we'll go through and show the different chemicals that are involved, the different processes that are involved in just using shaving cream, just creating the shaving cream. And if you ever go to the store and you pick up a can of shaving cream and you take a look at it, on the back you'll see all these ingredients. And I went through a lot of chemical engineering, and I will tell you, when I graduated school, I could look at the back of this and not have any idea of why those chemicals were actually in there. And at the time, I didn't even know what some of these chemicals were. But I had a lot of chemical engineering education, and one of the other things one of my other goals is to show you how chemical engineering knowledge is extremely useful for designing chemical products, especially when you couple chemical engineering knowledge and knowledge about physical properties. If you think about it, as a chemical engineer, a lot of times we're taught how to build or design a chemical plant. So we learn about things like distillation columns, absorption columns, heat exchangers, reactors, pumps, pipes, valves. When you think of designing a chemical product, there's pieces also. There's parts that we put together to make a product. We put together freezing point presence, corrosion inhibitors, solvents, thickeners, surfactants, colorants, and sometimes we try and blend these together into a formulation, or sometimes we try and build all this function into a single unit, which for us would be a single chemical. And so what I really want to show is that when we think about chemical products, it's not going to be that different, or you won't need to learn that much. Well, your basis understanding of chemical engineering will be very useful. You'll understand understanding reaction equilibria, light absorption, phase equilibria, things of viscosity, fluid flow, rheology. You'll see that they're both applicable to designing processes and designing products. So with that, let me start talking about a very fun chemical product. What we have is a ballpoint pen, or specifically the ink within ballpoint pens. if you look in the U.S., there are patents that go back to the 1800s for ballpoint pens, and it's a simple concept. You basically would have a a container, basically the tube that holds ink. The ink has to have certain properties, and at the end there's a ball, and basically the ink coats the ball, and the ball rolls on a surface and deposits the ink. The interesting thing is ballpoint pens came up in the 1800s, but it wasn't until about the 1950s they became popular. And it wasn't a problem with the pen. It was a problem with the ink in the pen. That was what important. And if we take a look and just think about ballpoint pen ink, we have to think, what does it actually have to do? It has to do a lot of things, actually. The main thing for a ballpoint pen is it has to stick some kind of colorant onto a piece of paper. So you can imagine we have, let's say, a bunch of pigments, little tiny particles, and we want that glued onto a piece of paper so we can see what we're writing. So that sounds okay, but we also have to understand that these particles have to stay in the ink, sometimes for a long period of time. We don't want them settling out or clumping together, and the ink itself shouldn't degrade. It shouldn't break down over time or break down because of biological activity. So we have to have that ink just right. The viscosity has to be right. We want to make sure the ink flows out nice and smoothly when we want it to. So we want the ink to stay in the tube, so it has to be kind of thick, but it has to flow out easily. So it has to be kind of thin at the same time. So we have to figure out how to accomplish that. The pen itself contains many metals, so we want to make sure the ink doesn't react with metals. It has to wet a paper surface, which means it has to be able to spread out on a paper, and it has to evaporate quite quickly. That's the thing that's most amazing. You write on a piece of paper, and within a few seconds, if you touch the ink, it should be pretty dry. And it has to form a tough film. If you ever think about it, the ink you put on a piece of paper, if you fold the paper, the ink doesn't break off, or it shouldn't. So all these requirements, all these constraints on this one simple product, this ballpoint pen ink. So how would we go about actually designing this? Well, one of the things that's fun is you look at how the other people design things. So this is an old patent. And one of the things when you work on products, you look at many patents, you look at what other people came up with. And as a chemical engineer, once again, I look at all this long list of chemicals, and especially in this case, things like, Sunspurse Black, Cobra-Tech, ethylene glycol, I know what that is, but many others I don't know what those are, and I would have no idea why they're in there. But if you start thinking back to our constraints, that should give you some hints of why these ingredients are in the product. So here's a list of ingredients, but if you say, well, instead of focusing on the individual chemicals, we go back and saying what has to be in the ink, like we said, our design constraints. And we realize that our ink has to contain, again, a colorant. It has to contain a corrosion inhibitor because it's basically in contact with metal. We put pH adjusters in case chemicals are in contact with metal. It has to wet a surface. There has to be a solvent to keep everything moving and then evaporate. And we put in a certain thickeners, antimicrobials, so it won't degrade. And we put a polymer, which basically acts as the glue to glue our particles or our colorants onto the surface. So this is one of the key things. Again, as a chemical engineer, when you look at this, all the chemicals, yeah, there's always many, many chemicals. But if you think about what has to happen, then you'll see that to accomplish our design tasks, we have to have certain ingredients. We have to have certain ingredients that do certain functionality, and then we can worry about the actual chemicals that give us that behavior. Once we say we need a certain thickener, then we can figure out what thickener we should pick. So you can see there's this two-step process. And what's useful when you go through this two-step process, and if you step back, it's the same thing when you pick a pump. When we pick a pump for a process, we don't start out by saying, here's a catalog of pumps. We go by designing, what does the pump have to do? What's its throughput, basically materials of construction, pressures that are involved. It's the same thing here. We would say we need a thickener that behaves a certain way. We need a solvent that evaporates at a certain speed, a certain rate. So first we design the general category, then we worry about picking the actual material. And this is useful because we thought about ballpoint pen ink. What about similar products? What about a paint or a cosmetic? If we think about mascara in some sense seems like it's similar to an ink. It's supposed to coat a surface. In this case, it's a particular hair, and it has to have a certain color. And if we go through, here's a formulation for, again, a common mascara. It has very, very different ingredients, though, from what we think of a ballpoint pen ink. However, if we look not at the ingredients, but at the purpose of each ingredient, then we'll start seeing that, again, this has a thickener, it has an adhesive, has preservatives, solvents, colorants, has an emollient, which is a new thing, but it has a wetting agent or surfactant and a solvent. So again, you would think if we focus on what has to be made, or what the tasks are that have to be accomplished, you can see it's very, very similar. If we focus on what I say is the physical properties, we don't care about the actual solvent involved, but we know it's a solvent that has to dissolve things and has to evaporate. If we focus on the properties, then we have an easy way of addressing all kinds of different physical chemical products. So that's the main concept I really want to convey here, is that physical properties are the key. Don't focus on the chemicals at first. Obviously, we have to pick them later, but you focus on the properties at first. And then once you have the physical properties, then we go about trying to say, what are the actual chemicals that have those properties? So what I want to do is just kind of show how you go about doing this, and we'll talk about a few other physical properties. Basically things like light bulbs, shaving creams, aircraft anti-icing fluids, and even artificial blood. And these are sounds like very varied properties, but I'm going to show how we can basically understand these. If we look at, these are very varied products, but I want to show how we can understand these if we focus on properties. At this point, I just want to make sure that I'm coming through okay. I don't want to end up just talking to myself for a while, and just wanted to check in if there's any questions or any issues as far as the presentation goes. So I don't know, Veronica, is everything sounding good?
Well, I think it's better you go ahead, and after people may ask.
Sounds okay? Very good. All right, thank you. So let's just quickly go through some of these. One product that I enjoy very much is a light bulb. And people don't often think about light bulbs. I have one here. But if you think about light bulbs, they're a very intriguing chemical product. If you think what a light bulb has to do, it basically has inside a filament and made of tungsten that's heated up to extremely high temperatures, 2400 K. This is one of the hottest temperatures on Earth. The original light bulb, they put tungsten inside a glass, which is a soda lime glass container, and they pulled a vacuum because at 2400 K, the tungsten would react with oxygen, so they didn't want any oxygen in there. What would happen over time, though, is they noticed, oh, let me skip ahead. Over time, the glass would turn dark and the light bulb would fail. The tungsten filament would break. And so as a good chemical engineer, you have to look at this and you say, well, what was happening? Again, over time, tungsten would shine brightly, and then the glass would get darker, and then the tungsten would break. Well, if you think about it, we have an interesting mass transfer problem. What was actually happening is if you look at the vapor pressure of tungsten, and people say, well, tungsten's a metal, but it still has vapor pressure. And especially at 2400 degrees, you would actually get some of the tungsten evaporating. And once the tungsten evaporates, here's what would happen. If we look here, we have kind of on the top view, we're looking on the left at the tungsten filament at 2400 K. We have a cold wall. It's colder at 600 K. So in essence, the tungsten would evaporate from the metal and basically deposit on the cooler wall. So over time, all the tungsten would continue to move toward the wall, and you would end up with less and less tungsten, more tungsten in the filament, more and more tungsten on the wall, which would get darker and darker, and then finally the tungsten would fail. So as an engineer, you start looking at this and saying, how can I model this process? And you can just look at Fick's law, a nice diffusion based process, and you can go through, solve this, and in the equation, you have the mass transfer rate basically as a function of the vapor pressure of tungsten, pressure inside, the distance, various things. And this is what's wonderful as a chemical engineer. You have these equations, and then you can start looking at it, and you can start saying, how can I use this equation to help design a better light bulb? How do we lower the flux, NT, which is the flux of tungsten from the filament to the light bulb? Well, my focus is, again, on physical properties. So you can say, well, what physical property can we change in this equation? And in this case, this is the diffusion of tungsten through the light bulb. And originally they put in a vacuum, but suppose we put in something else, something to get in the way. How could we lower the diffusion coefficient of tungsten through, let's say, a gas? And if you look at the models for diffusion coefficient, you have this nice complicated equation here, which you don't have to worry about. The key part you have to look at is in this equation, this estimates the diffusion coefficient of tungsten through gas, and we say it's a function of a variety of parameters and the molecular weights. 1 over the molecular weight of tungsten plus 1 over the molecular weight of the gas. And if we pick a variety of gases, like we show here on the right, nitrogen, argon, krypton, xenon, we can calculate this sum, this ratio sum. And we want diffusion coefficient to be low, so we should have our ratio be low. And you can see here, nitrogen has a nice low number, argon's better, krypton's better, xenon's better. So as we get a heavier gas that gets in the way of tungsten, it works better. Unfortunately, if you look at this table, we can see that not only as you go down the table do you get better performance, but you also get higher cost. And so thus, as a good chemical engineer, you have to try and optimize this. How can we get good performance while having reasonable cost? And so it's just a standard chemical engineering design problem. So we weren't the first, or I wasn't the first one to think this up. In 1916, a researcher by the name of Irving Langmuir, who's very famous in surface chemistry, got a patent to do this. He was working on light bulbs, and he basically came up with the idea of putting in a gas that would extend the life of light bulbs. And there's a lot of other surface chemistry involved in the filaments of light bulbs. He went on for halogen light bulbs and went on for much, much more contributions to surface chemistry. So again, physical properties and chemical products help you come up with many ideas for many areas. I'm going to hop from light bulbs to artificial blood. The idea of artificial blood is that human blood is needed for medical operations, procedures, emergencies, but it's has very limited shelf life. It has to be stored very carefully, and there's not a large supply at times, and other issues. So it'd be really nice if we could make something to substitute for human blood when needed. Just like we did with our pen, we go through and say, well, what does it have to, what would this blood substitute have to have? Main key thing, blood has to absorb or carry a great deal of oxygen and carbon dioxide. It has to be obviously compatible, with blood. It cannot have other bad side effects, and it has to be able to be stored for a long time. One of the key things, let me hop back here. If we then say, okay, what chemicals have high solubility for blood? I'm sorry, what chemicals have high solubility for oxygen and carbon dioxide? We see that perfluorinated compounds seem to be the best. And they have very good solubility for oxygen, a good solubility for carbon dioxide. But if you look at these chemicals shown here, perfluorocarbons don't seem to be very polar. In fact, they're very non-polar chemicals. Blood itself, it's in essence salty water, so it's a very polar substance. And so we kind of sit there and say, okay, how are we going to mix this non-polar chemical with this very polar chemical? And this is, again, the same way in a chemical process. When we see certain situations, we say, we have to distill this or we have to extract it. Whenever you try and mix very different chemicals in a product, you typically say, well, we have to use some kind of, let's say, an emulsion or dispersion or such. And invariably, that means we're going to have to use some surfactants. And in fact, this is what we do. We basically create a emulsified system in which their oxygen carrier is in the middle. So this is our perfluorocarbon. And we have an emulsifier phase. This is our surfactant that surrounds the perfluorocarbons so that it can basically be dispersed within our continuous phase, which we say is mostly water. And if we look back, let me hop back here. We see in this table an example formulation of a blood substitute. It has many, many different complicated chemicals in it. But if we go step by step, here's our oxygen carriers, something that carries oxygen and carbon dioxide. Here's the emulsifier phase. We have to make this compatible. We have to make an emulsion. We need surfactants. There's some tricks we play sometimes that in this surfactant phase, we actually want that layer to be very thick. So we dissolve polymers into that phase to make it more stable. And we want it, when we make the artificial blood, it's going to be in a continuous phase that should be compatible with blood. So we have to put all these different salts and so forth to make sure it works out well. So even a very complicated formulation like this, basically, if you go step by step, look at the properties of what has to be accomplished, you can understand what's going on. And just real quick, one of the issues when you make a dispersed phase, if you make an emulsion, you can imagine we want our drops to stick around for a long time. There's various issues where drops will settle or drops may grow, something called Ostwald ripening, where big drops get bigger. I won't go through the equations, but basically what happens is because there's a higher activity of chemicals inside a small drop because of the higher curvature of the drops, you tend to have the contents dissolve into the continuous phase at a faster rate than they dissolve out of into the continuous phase from a larger drop. And so you end up with big drops actually getting bigger, small drops getting smaller. And this is called the Kelvin effect. And again, you can go through the calculations and you can actually calculate it how fast, let's say, a drop will grow. If we look at this equation, the same way we did before, we see that it has various terms for how fast it grows, the size, surface tension, all this, but there's a particular physical property in there, the diffusion coefficient. It makes sense that the rate of growth is dependent upon how fast a chemical can diffuse from the small drop to the big drop. So how can we basically slow down this diffusion process? Well, we saw this when we looked at light bulbs. How can we basically get this chemical to move slowly or slower from the small drop to the big drop? We can change the diffusion coefficient. Now, this is a diffusion coefficient of a chemical through a liquid phase. So there's different models for this than a chemical through a vapor phase. And if we look around, we can see that the diffusion coefficient in this case is a function of molecular weight, function of density, function of viscosity. And if we increase the viscosity, this is eta, the diffusion coefficient will go down, which makes sense. A thicker solution will mean that the chemical will have a harder time, or it'll have to take longer time, I should say, diffusing. And this is one way we can stabilize the emulsions. We can make it thicker by looking at the physical properties. Excuse me. So in these two presentations, in these two products, we looked at how we can kind of analyze and understand the physical properties and how they affect the products. We're going to go to the next step. We'll take a look at shaving cream and see how we can actually start using our property models to dream up products or maybe find substitute products. Shaving cream is truly an amazing product. If you think about it, you basically shake up a can. This is what's called a foaming shaving cream. So shake the can, push the button, and a foam comes out. So how does that actually work? If you look at the ingredients, you'll see that we have sodium lauryl sulfate, triethanolamine, all these things. We have isobutane, propane, and we have water. Once again, isobutane, propane, non-polar chemicals, water, very polar. If they're in the same product, that means that probably all the other stuff in there has to be surfactants of some kind. So we know that we're starting out with a dispersed system of some kind. So how would this work? If you look at shaving cream sitting there, there's actually three phases. Phase A is a vapor phase, and probably the hydrocarbons, the isobutane, propane, and some water would be in the vapor phase. Imagine this is sitting at room temperature. B would be a liquid phase, and it's probably the under pressure. Isobutane and propane would be in the liquid phase. They're less dense than water. And then we would have the water phase. And the water phase would contain water, probably the surfactants, but the surfactants probably would be right at that interface between phase A and phase B and phase C. But this is unshaken shaving cream. So now we take the shaving cream, shake it up, and we actually end up with two phases. We still have our vapor phase at the top, but our phase D is now an emulsion. We basically have a phase D2, which is our continuous phase, and D1 actually contains our hydrocarbons. So our hydrocarbon surrounded by a surfactant in a continuous aqueous phase, somehow similar to our artificial blood. The intriguing thing is when we push the valve and this stream comes out, we now have a stream of basically water with some hydrocarbon particles inside. We want this to make a foam. So the idea is inside the can, we're at a relatively higher pressure. The hydrocarbons are a liquid. If we pick just the right hydrocarbons, when the foam comes out at a low pressure, those hydrocarbons will vaporize. And so this is what we do. We actually go through and we look at the vapor-liquid equilibrium diagrams. This is, if you look on the right side, this is vapor-liquid equilibrium phase diagram, propane isobutane. I picked 20 degrees, about room temperature. This is a pressure versus composition diagram. And point 1, we're saying inside the can at a higher pressure, we want our hydrocarbons to be a liquid so they can be coated with our surfactant. And then at point 2 indicates atmospheric pressure. So when the stream comes out, the pressure is dropped. Hydrocarbons would then be in the complete vapor phase. And what we can do is we can look at different mixtures, different hydrocarbons or pure hydrocarbons. We don't have to do a mixture. And we can see if we can get just the right phase behavior. And in fact, if you go through this, you'll find out that propane isobutane has just the right physical properties to give you this kind of behavior. But there may be other chemicals that give you even a better behavior. And this is a way of using, again, our physical properties or chemical engineering knowledge to say, hey, how could we find a nice chemical or a nice mixture that, again, at a reasonable pressure, just a couple atmospheres, is a pure liquid, and then at atmospheric pressure is a pure vapor. So, interesting combinations. Let's look at another kind of shaving cream. This is what's called a post-foaming shaving cream. So this foams only after the shaving cream is applied to the skin. What happens is, again, we look at a formulation, many ingredients, and seem very, very different than the other kind of shaving cream. But if we look at it, we have colorants, which we didn't have before. We have fragrance, which we didn't have before. Okay, so this is making it look nicer. We have all these thickeners in there. Well, this is a nice thick gel, so that's probably what this is in for. We have similar chemicals to what we had before. We had these aloe, water, and again, we see, in this case, isopentane and isobutane. So these are hydrocarbons and water. So it seems like things are going to behave just as they did before. We have a hydrocarbon and a water and surfactants. However, what we want this product to do is actually come out as a gel and then foam afterward when it's rubbed on the skin, rubbed on the face. And so once again, if we look at different phase diagrams, and we end up looking at different hydrocarbons in this case, we'll see at point 1, this is now a temperature versus composition vapor-liquid equilibrium diagram. So again, at low temperature, we have a liquid condition. So actually, if we choose the right composition, it'll come out of the can as a liquid. Then we want it to vaporize. So the question is, well, at what temperature do we want it to vaporize? At point 2, we want it to vaporize at the temperature of the skin. So in essence, what we're going to do is pick a liquid, in this case, a hydrocarbon mixture that's designed to boil at the skin temperature. And people often ask, well, where's the heat come from? In essence, it comes from your face. You're boiling this hydrocarbon mixture so that it would vaporize, surrounded by a surfactant, and that's what makes the foam. And once again, once we look at the vapor-liquid equilibrium diagram, we have our temperature limits. We can pick different chemicals, different mixtures, different compositions, and try and find just the right one that works well, that gives us a nice big vapor at skin temperature. And of course, as an engineer, we also have to check out the costs and other properties associated with that. All right, just two more, or actually one more example of a chemical product. This is something called aircraft anti-icing fluids. In many parts of the world, it gets very cold in the winter months, cold enough where we have ice and snow that will land on aircraft. And for an airplane, the wing is very important that it's a very smooth surface. Any accumulation of ice and snow disrupts the airflow, and a disrupted airflow causes loss of lift, and which is very important when the plane's taking off. That's we need a tremendous amount of lift. So what we do is we actually put a layer of, you can think of it as antifreeze. It's a layer in which incoming ice and snow will melt, and that way you won't have any accumulated ice and snow. One of the tricks, though, is we have now a layer of antifreeze. That also isn't good. So somehow that has to come off before the plane takes off. And what we actually do with anti-icing fluids, we design a liquid that has just the right viscosity. It's thick enough that when it's not being used, it just sits on the aircraft wing. But as the plane starts taking off, the viscosity drops and it'll shed off the wing so that the wind from the takeoff will basically pull all the anti-icing fluid off the wing. This may sound somewhat familiar to our ink in our pen situation where we wanted it to be thick and we wanted it to be thin. Same case here. So if we go through again, we look at our different requirements for our anti-icing fluid. Obviously, we don't want it to be toxic. We want it to be safe for the environment. It should not be flammable. One trick, whenever you want something safe for the environment and not flammable, is to use water. It's a wonderful addition to most products. It also kind of reduces the cost for most products. It can't be corrosive. We're going to put it on airplanes. So we're going to have to put a corrosion inhibitor in here. It has to wet a surface. So again, wetting a surface or making two chemicals compatible, in this case, water and a usually aluminum surface, we need a surfactant. We have to add a colorant just so it's easy to identify what chemical to use. And then we have pretty much freezing point depressants. So now we can go through and do some chemical engineering. If we look at the freezing point depression, we can do, in this case, a solid liquid equilibrium diagram. And I showed a diagram here for ethylene glycol and water. And in essence, if you make a specification, you could say at 25 degrees C, so this is again solid liquid equilibrium diagram, temperature versus composition. At low temperatures, we have a solid. Above the curve, it's a liquid. In essence, under the curve, to a certain degree, we have a two-phase system. But on the curve at 0.1, you could say, well, if we have this composition, which you can read off at 0.2, I can say that that composition of ethylene glycol and water will not freeze until minus 25 degrees. So this is a way, again, we can go through looking at different chemicals, different solid liquid equilibrium diagrams to see what chemicals would work and to figure out maybe if we can get replacement chemicals. It's a way of designing and screening different chemicals. The clean wing on rotation, in other words, clean wing as the plane starts taking off, same approach. Think of the ballpoint pen ink. And what we use in this case, we think of a shear thinning fluid. We think of something that we can add in to cause the viscosity to be thick when there's no shear. And then when the plane starts taking off, the air passing over the wing will cause high shear and cause the viscosity to drop. And in fact, we use what's called a type 4 fluid. We put in chemicals, everything from xanthan, gum, and so forth, that will cause a power law fluid, or will create a power law fluid, so the viscosity will drop quickly. And this is an example formulation. Oops. We have things like propylene glycol, which is our freezing point depressant. Turgitol is our surfactant. Triethylamine is our corrosion inhibitor. Carbapol is our thickening agent. Chilling green is green, causes it a colorant. And water is our solvent. So once again, the idea is that if you start looking at the properties, all these products start making some sense of how they're designed and understanding how to design them. I just have a few minutes. I just wanted to say that was the first part. We talked about looking at products and figuring out how we should design them in terms of their excuse me, physical properties. How would we go about the second part? Once we have properties, how can we go about making something that has those properties? And let me just use a quick example. The idea of what's called a paint remover or a paint stripper. If you have a painted surface, you put a certain chemical on, what happens is that chemical soaks in to the paint and actually causes the paint to swell. And the paint you consider a polymer. As the solvent dissolves into the polymer will swell. It causes forces inside the polymer, and those, if you pick the remover correctly, those forces will be greater than the adhesive forces, and the polymer will actually swell and wrinkle and fall off the surface. If we look at a common paint remover, it's N-methylpyrrolidone. And if we look at its various properties, we can say, well, okay, I guess this is a good chemical. We know from experience it's a good chemical. Unfortunately, for various reasons, people want to replace this chemical. So what might we come up with? We might say, let's dream up a new chemical. Would it have the same physical properties as NMP? If it has the same properties, like we're saying, it probably will have the same performance. So we could always go and measure this, but if we want to evaluate dozens or hundreds of chemicals, we would have a very long time to do that experimentally. Fortunately, we can use physical property models, specifically group contribution techniques and equation-oriented techniques. Well, let me just briefly go through what each of these are. You've probably been exposed to these. Group contribution techniques have the idea that given a molecule, we can break that molecule into groups, and that each group will have a certain contribution. So in this case, we can see we take our molecule, we can break it into CH2 groups, CH3 groups, CH2 groups, CH groups in a ring, CH groups again in a ring, oxygen in a ring, and a CO group in a ring. Each of these pieces contributes a certain amount to a physical property. In this case, the boiling point. So if we look at each contribution, CH3 has a contribution of 23.58. If we total these up, we can get an estimate. So in this case, we can dream up a new molecule and we can estimate a physical property. Once we have a few physical properties, there's equation-based techniques which let us estimate more. Here we have a model for the vapor pressure that's dependent on properties like boiling point, critical temperature, and critical pressure. So if we know these values, we can estimate the vapor pressure. What's nice is many of these basic properties we can get from group contribution techniques. So now we have a general idea. If we want to design an NMP replacement and methylpyrrolidone replacement, we can say, well, here's the physical properties of NMP, and we give it a certain range. We say, well, if it's close to those physical properties, within a min and max, that looks good. We can dream up a new molecular structure, use group contribution techniques, equation-oriented techniques, check to see if the property's in the range, and we can have maybe a new chemical. So, for example, we can pick this chemical shown here, just dream it up. We go through our estimation techniques, get boiling points, critical temperatures, critical pressure, use group contribution techniques for those properties, use equation techniques for vapor pressure, and we can check. The estimated vapor pressure for our new chemical is 27. That should be pascals. And the estimated vapor pressure here, the range is between 11 and 51. So this looks good. In fact, it looks very good, and we can keep doing this over and over again. We can dream up a new molecule, but it will take a long time if we keep estimating one by one. So quickly, just what I want to show is what we're able to do is teach the computer how to create molecules. We tell the computer basically, here's all combinations of two groups, and what the computer, here's all the combinations of groups we want to make molecules from. So the computer will pick all combinations of two groups and try and make molecules from those. It will then go about all combinations of three groups, in which in this case there's 680 ways of picking all these groups 3 at a time. Likewise, combinations of 4 groups, and so on. Now what happens is we have to tell the computer if you can put these pieces together, and there's some very simple equations that show that if you take a group of pieces of molecules, they have to satisfy the equation shown here, where B is the number of bonds, N is the number of groups. We total things up, and we can see this first collection of groups cannot be connected together. There's just not enough places where we can connect things. However, the next set of groups, we can. So now we have a way where the computer can take pieces, put it together, and check to see if these are valid molecules. We tell computer also that there's certain kinds of combinations of groups we don't want. And we actually can make a computer system that will automatically put together molecules, see if these are new molecular structures, estimate the physical properties, and check if those properties are what we want for our new product. So again, what I wanted to do today was talk about physical properties and their importance in designing chemical products. We went over a number of different chemicals that, a number of different products that hopefully at first looked very, very different, but now you can start seeing that they're all somewhat similar. And again, the main concept, focus on the physical properties. Those are key. So hopefully I accomplished some of my goals where I was able to show you how we go about understanding chemical products, designing them, and hopefully next time you're in the store, take a look, see what's on the back, and start thinking what might be in there. Again, with that, I'd like to say thank you. I'll be very happy to take any questions, and I'm always very happy to talk about products. And I have my email here, or we have our website where we have information on our software and physical properties and chemical products. So with that, I thank you and be glad to take questions.
Thank you very much, Kevin. And let's see, people, you were invited to make questions. It was a very good presentation. Wonderful.
Thank you.
And the idea is to go directly, try to make a product. I don't know. I have a product that I would like to be in hands, but I don't know if the computer will give me, but I'll try.
And this is what's fun too. I mean, in designing products, if you look at actually the industry, there are obviously huge companies that spend a great deal of time and effort coming up with products. But there are many, many small startups. People have a very good idea. They say, hey, I think this combination is something that people would like, and nobody's worked at it before, and it works. There are always wonderful new products coming out all the time.
Yeah. It's really something that we have to look at in details, yes, as you mentioned. Yep. People, please go ahead.
May I have?
Sure.
Thank you for very nice presentations and very didactic problem. Let me ask you 2 questions. One is, you have shown properties that are very simple to calculate, like critical point, critical pressure, critical temperature. But you have shown very complicated applications like emotions. So how can you use this, can say simple technique, calculate a property for emotions that are very complicated? That's my first question. Can I ask the second one? You
sure.
Can answer. Another question is, what do you think about use molecular simulation? Like you see that chemical engineer data now raise molecular simulation as a kind of experimental information. Right. we know that it's not that far, but as well, we know that we have some very nice information that can take from molecular simulation. So we are not that far, but not that it's not so bad.
Right. Yep.
So
Now,
comment on these two topics, please.
Sure. Excellent question. And I think one has to look at the overall approach. If we're designing, let's say we're designing a new shaving cream and we're looking for new surfactants and such, the idea of how can you go from the molecular structure of surfactant to saying how well it would work inside a shaving cream is, those are complicated models. What we try and do, like any kind of design, we start out with the space of all possibilities. And we'll say, well, can we use any good, what we call inclusive models? So we don't want to throw away good ideas, but can we use simple models to kind of narrow the space? And when I say simple models, I should say quick models. Can we use quick, inexpensive models to narrow the space? And that's what I showed here. Now, when you have a smaller number of combinations, we can use more involved models or detailed models. The molecular modeling works very well in many applications to say, I still can't determine, let's say, the stability of my emulsion from just first principles, but maybe I could determine what makes an unstable emulsion and get rid of those possibilities. Because our opinion is always, we start out with just our ideas. We can say, well, I don't want to include chlorine because it's, at least around the world, it's regulated, so we get rid of those possibilities. Then you might say, well, I need to have a certain evaporation rate. I can use a simple model that narrows it. Then I can use molecular modeling, which in some cases can give you good numbers, but in many cases you can say, at least I know I can identify the ones I don't want. And then ultimately, I still believe we have to do the experiments, because the experiments are the one thing that can surprise us dramatically. It's if it's not included in the model, it will be included in the experiments if we do it correctly. So that's the one thing that's fun. But I like all levels of models. It's just we try and use it when we're considering, millions of possible candidates. Let's see how much we can narrow it down with our least investment of time and effort for models. The one thing that I will say what molecular models are very good at is if they can do nice work with properties, but I like systems with molecular models. So for example, if you're looking at an emulsion and you're saying, excuse me, I'd like to see how over time, maybe this emulsion will coalesce. That's a beautiful modeling effort. And people have done this kind of work. How will the different size emulsion particles basically distribute themselves and move? And those are beautiful applications of the modeling, which I think, again, chemical engineers should be aware of. But it's the same way you think of distillation columns. We have shortcut methods that, get you somewhat close. So at least you can think, is it worth doing distillation? And then if you get that answer, then we can go to a little more detailed models on that. So I think modeling is, at all different levels is very, very good. So I hope that addressed.
Thank you.
No, thank you very much.
Thank you. Who else? Come on, people, don't be shy. Let me ask you something indirectly. Like, do you still teach at some university there?
No, not anymore. I had wonderful opportunity for 5 years, and I give credit to all the professors. It's a lot of effort, even after doing it for a couple of years. And you would think, oh, I just do the same thing over, but it's not. And it's for me, it was a good learning experience. I thank all the students for helping educate me on how to teach the product design. But it was the one thing about teaching product design was very fun, is that many of the students came to the class with an interest in certain products. And so we would often have discussions. We would had people who like to do art. So we would talk a lot about paints. And we had people, many who were interested in cosmetics. And so we would talk about different cosmetics and such. And somebody who was interested in actually, coatings of paper cups. And so that was, for me, very fun, because it was, again, testing my just experience of saying, here's how we can go through a process and teach everyone, how to go through the process and think about all these different products in a systematic way. But I think for me, 5 years was good. And I enjoy teaching about this, but it was just a bit too much of dedication of time and being also employed elsewhere.
We have a question here in the chat. Victoria would
Yep.
like to make a question.
Sure.
Yes.
Oh,
Go ahead.
I know it depends. First of all, Kevin, thank you very much for that inspiring, and you made everything that seems very simple, and you know that it's very complex.
Sure.
But my question is, how long does it normally take from the first screening until the validation of the molecule at lab, until the first proof of concept at lab? I know it depends on the challenge, but would you say like it takes 1 year, 2 years?
Sure. It's I think what's interesting is if you look at it from, let's say, a company point of view, many companies will allocate, let's say, about a year and a half, so 18 months.
Okay.
And if you're starting a dramatically new product, that may take longer. But just from how much time a company might be willing to say, and we're not talking about basic research, but let's say if you want to make a new, let's say, fertilizer. So you have an idea and say, we want something that one of the issues of fertilizer today is you have a lot of runoff, it gets into waterways, and that's bad. So you may have an idea and somebody may say, okay, I'll give you 6 months to come up with some, proof of concept. And then that's where, again, instead of looking at the entire product, you might just say, okay, what do I need just to prove this works? So maybe I want a coating on my fertilizer particles. And then you'll get another 6 months of saying, see, this is, it really does work. And then the last part is always, okay, how will this fit in to a product that's going to be sold, going to be used by everyone in the world? That's the difference also that's fun about a chemical engineer. We make chemical plants and we expect people to learn how to use chemical plants. We put them far away from everybody else. When you make a product, it's in everyone's hand. And for the most part, the products have to be automatic. In other words, the shaving cream has valves, it has pressure, it has mixtures, it has to work without any help. And that's usually this last part, and where you say, okay, this is a good product. You worry about how it might be. There's an old saying, when I was starting out, I had an old engineer who said, never design a product for how it's going to be used. And I was like, of course you design a product how it's going to be used. He said, no. Figure out how the product might be abused, might be used in the wrong way. And that puts a lot of constraints on it. And that's usually what this last part is. You can say, okay, it's a very nice product. What happens if people keep it for more than 1 year? What happens if people keep it in the shed at high temperatures or in the trunk of the car at high temperatures? Many of these other constraints have to come in. But usually you'd like to say after, let's say, about 18 months, 2 years or so, do we have a product in some form? And then if if it makes economic sense, you try it. If not, well, if it makes economic sense, you try it out, and then you keep, hopefully improving on that. But there's many, what's fun, we were talking at the beginning, many other disciplines, mechanical engineering, industrial engineering, they go through these product design courses, and they teach the steps of product design. Now again, I gave it kind of product engineering where we actually have to make this stuff, but it's very important to kind of pick out those key criteria, which are either you go or you don't go. So you pick out the key things and say, in 6 months, if I can't figure out how to do this, then we stop the project. And which is always handled differently. There's some companies who love ending projects. They celebrate when they either make a product or when they end a project.
Yeah.
Because either way,
That
it
fail.
means, it's good to fail fast.
Yeah, exactly. The fail fast.
Yeah.
Yeah, we
Yeah.
work a lot with this in our research institute, and this is something that the timing is very relevant when we want to sell the solutions for companies. Sometimes companies brings the challenge, but
Yes.
they are but we sometimes we don't have an idea of the timing. So to have this perspective from you, don't expect anything lower than I don't know, 16 months, because 18 months is already something that is very reasonable
Yeah.
and
Yeah.
the common.
Yeah. It's there's a lot of fun aspects, business aspects, I should say,
Yeah.
to the product development and such. But I think the key thing is showing how some of the hardest constraints can be addressed, because that's always the issue. And the other thing is there's lots of stories I like collecting of people who didn't give up. They basically had an idea and it didn't seem to work. Again, Post-it pads and things like this. It might not be a product, but people who kept that in the back of their mind. And institutionally, as a company, I don't know how you do that, because people leave and such. But the products that didn't work at the time, it would be nice somehow to capture that. I don't know how to do that, but there are those stories. But from a practical point of view, if it's not working out,
Yeah.
I'd like to find out quickly. No, great questions. Yeah.
Yeah. Thank you.
Yeah.
Thank you very much.
Thank you.
Thank you, Victoria. Vanessa, go ahead.
Hi.
Hello.
I never worked with theoretical modeling, but I would like to begin. And what's your advice to begin? And it is possible to figure out which molecule will suit better to a very new product through a specific need from zero?
Right, and it's a great question. I don't have the best answer, but what I will say is it's a very nice time. There are many software products that are either open source or have different versions that are available for free and such. So if you look at everything from software like we have for let's say group contribution models, equation of state models. There are different software packages out there that do molecular modeling work, molecular dynamics type models, and then there's quantum level models. Starting out is I've been asked that a bit, and I don't have any specific advice, but I think within your own university or within a nearby university, I should say, you can see what kind of courses they might use in some of these what kind of software they might use in some of these courses they teach. The key issue always though is that first step we talked about, looking at a product and trying to say, okay, if I want to make again a new windshield washer fluid, what's important in that? And if you sit down and you think, what does it have to do? Well, it has to wet surfaces. It can't dissolve the paint on your car, and it has to dissolve things that stick to a windshield. So you're trying to figure out what's the composition of bugs that are stuck on your windshield, and what are the chemicals and bugs that are squished that you want to dissolve type things. And once you come up with that, then you can probably say, okay, I want to do, let's say, solubility modeling of different chemicals. And so I think if you just look around and say, how can I do solubility modeling, it'll identify a number of theoretical models and software tools that might be able to help. So it's a very broad field, and that's I apologize, I don't have a really good answer of how to get started, But I will say that today's a lot easier than it has been, because there's a lot of tools that are out there. Yeah. Good. So sorry, it's a good question. I think right now, just, picking up some tools and trying them out might be the best way to see what what these might be able to do. Good.
Okay, thank you. Kevin, there is Oscar, please.
Thank you, Kevin, for your nice presentation. It was
Thank you.
pretty clear. You went deeply, but very clear. It was really nice.
Thank you.
And what I would like to know is about your team. You mentioned a lot about chemical engineering.
Yes.
But what other specialities work with you? Because I think the first step is to understand what the customer wants.
Yes.
And so, which other specialties are in your team to keep this ball running fast?
Yes. Yeah. And it's excellent questions. And like we said before, if you think of just product design, let's say from a company point of view, it's I mean, for many companies, it spans the entire company. I mean, that's what they would do. And so obviously, something that as an engineer, when we talk about things like marketing and sales, a lot of engineers say, oh, I don't want to get involved with that. I hope you get involved, because that's usually very important for making the money that pays your salary if you work in a company. But I like to say that, okay, let's say the marketing people said, there's an opportunity for a new paint remover. On the specific teams we usually work with, we will get that kind of input. And they usually have, let's say, some customers in mind. And when I say customers, we'll have an end user. The team is usually, it's made up of usually, let's say, chemical engineers, obviously chemists. And many of the chemists are looking at saying how they can make new chemicals. And chemists are amazing. We can find chemists that can make all sorts of new molecules. They just need sometimes some guidance on what to make. And that's where the approach we take can often help. Many companies, instead of starting from scratch, they might be saying, let's say today, applicable in Brazil, there's a nice need for new solvents that are sustainable, environmentally friendly solvents. So if we could start with, let's say, sugarcane, how can we make some new solvents from this for a certain application, let's say for a paint remover and such. And so we always would say, okay, what does that mean? I mean, what kind of chemicals can you make? So you talk with the chemists, the synthetic chemists, the analytic chemists. The synthetic chemists say we can make these kinds of chemicals. Then we are the ones who say, okay, if it's a paint remover, we can go through the chemical engineering and say what are the kinds of properties involved. And then we have to say, if we actually come up with some chemicals, how can we test these? And that's where the analytic chemists come in. And then in the end, if you say, okay, we can make this stuff, but it's going to cost this much, that's where you go back to marketing, and marketing says that no one will pay for that, so that we start again and such. So it's still on the engineering side. You get a little influence from, let's say, the business, but still working again with all the chemists and the chemical engineers and the material science people at times. So those typical specialties. What also happens that's also fun is you'll deal with many of the environmental people, or the regulatory people, who, at least in the US, they will say, nope, you can't use this. And you may ask why, and they say, I don't know, but you can't use this. Or the industrial hygienists or such who do actual tests on saying how toxic things are and so forth. And then we try and understand that. So it's a pretty good round. Unfortunately, as an engineer, a lot of times you come up with the idea, you make the suggestion, people say that's great, and that's sometimes the last you hear about it. But those are usually the kinds of teams we deal with. That's good.
And thank you. And one last question related to intellectual property,
Yes.
because you are working with really on the edge of
Yes.
technology, giving solutions for end product. How do you deal with the intellectual properties with these companies?
Sure, it's a range. So you could think when you and there's an area uh, they sometimes call this open innovation, as opposed to a company where everyone in the company is working on a product, everything belongs to that company. When you now decide we're going to form a project in which everyone has different contributions, it depends. In some cases, for us, we like to say for our particular company, the expertise we gain. So if somebody wants to design a new drilling mud or such for like drilling, you use different chemicals to basically seal the rock formations and such. We're probably never going to do anything with drilling muds and such, but understanding the chemistry, the physical properties and such, we're kind of saying, well, as we learn that we keep that. And then this company says, well, they don't care how it's made. They get a product that they'll sell. So it takes some negotiation in the beginning, but usually, and in some cases, we all say, all right, if it works out, we'll all kind of get a certain cut. So it varies, but it's usually surprisingly not too difficult. We usually, as people get into a team, they recognize there's a sharing of expertise. There should be a sharing of basically the results also. So, yeah.
Thank you. Thank you very much.
Thank you.
Thank you.
I don't know if somebody else, I know that it's late enough. I think we need to give you a break. I just want to ask you one question. What was the weirdest product that
weirdest.
Yeah.
Yeah, there's been a few. I think it's after lunch, right? For you guys. Good.
No, we still are going to have lunch.
Oh, okay.
For some of us.
Well, this I don't think this is too bad, but I had received a call once, and it was a gentleman looking for I don't know what it's called in general, but depilatory. It's depilatories. It's creams for removing hair from skin.
The wax.
And yeah, but this would be the kind of dissolves the hair.
Okay.
And I remember talking to him, and I said, "Well, it's hair is hard to dissolve. It's a really tough little chemical polymer there, proteins and all sorts of coatings." And when I talked to him, and we were just talking on the phone, and I said, "Well, one of the key things is that you can make a stronger and stronger chemical, but it might cause skin irritation." He said, "Don't worry about skin irritation." I said, it's a cream you're going to put on, let's say, someone's face, and it'll dissolve the hair, and it might hurt. He says, "Don't worry about it." He was a mortician, and so I guess when people pass away, the hair still grows for a few days, and
wow.
instead of shaving, he wanted to develop a product to use the hair removal. So that was
crazy. But here we don't have this problem because we don't wait days like in the United States. Like a ceremony with food, etc. My goodness, you're crazy. Could you do it?
That was what we talked for a bit, and it didn't go forward and stuff. But it was an interesting set of constraints for putting it on non-living skin and such. So that was the one that I remember. There were a few others that were interesting. Some people we worked with that worked for some people in the military who always have very bizarre requirements and such. They want something to work at all temperatures for all periods of time after being banged around and used by people who don't have the most education, so those have other constraints. But that was the one I remember.
Crazy, yeah.
Yeah.
Okay, great, Kevin. I don't know if somebody else wants to make a question, but it's kind of late.
Yeah, and I my email, I showed. I'm always happy to try and address questions and such. So feel free to contact me afterward.
Yeah, there is the email. I'd like to thank you a lot for this. You answered me so promptly and very, very good. Your presentation was wonderful. You explained very well, and then you showed all the complexity of this kind of desire, let's say like this.
Yeah.
Okay, very good. And I hope you can come to Brazil after
that would be wonderful someday. Yes.
next year, maybe.
Yeah.
And we can discuss something together, some project. We had people from some companies here in Brazil, and I hope they can interact with you if they need.
Oh, that would be great. Thank you.
Okay.
Yeah.
Thank you very much, and have a good day.
Well,
and,
thank you. It's a wonderful opportunity. I enjoyed it very much.
Wait for the invitation to come to Brazil next year, or when it's safe. Let's
when
say.
It's safe. Yes, that would be great. Thank you. Okay.
Bye. Thank you. And thank you, people, for the audience.
Yeah.
Okay. And let's see. This presentation will be in our site YouTube channel. Kevin, if you want in the chat, there is the address. If you want to see yourself again.
That would be painful, but I may have to do that. Yeah.
Yeah. And we have some other webinars, and
very good.
we are in September. In October, the first Tuesday of October, we're going to have another one, but it's from Professor Zevito about bioeconomy. Okay.
Very nice.
But it's going to be in Portuguese, Kevin. Then
that would be a challenge. Yes.
We have more than this product. Yeah. And we have a webinar from Professor Levinspiel.
Oh, yes.
No, it was not Levinspiel. My goodness, no, it's about kinetic too. But Professor Fogler.
Oh yes.
Yeah, it's we have it there. You can watch if you want. Thank you one more time, you, Kev, and the people who are attending.
Yes, thank you to everyone.
Bye-bye.
Okay, bye-bye.